Today we have the pleasure of exploring the fascinating world of 3D printing with Jared Wesenick from Compound Dynamics. Jared brings decades of expertise in machine design and manufacturing within the rapidly evolving field of additive manufacturing. And without further ado, let's turn it over to Jared.
Okay, I'm going to share my screen. So Anna, can you see that?
Yes, we can.
Okay. Well, as you said, I am Jared Wesenick from Compound Dynamics, and today we're going to be discussing large format additive manufacturing, or LFAM. So imagine scaling up a desktop 3D printer to produce parts the size of a car chassis or a boat hull, wind turbine molds. That's large format. Today we're going to talk about two technologies: fused filament fabrication, FFF, also known as FDM, and fused granular fabrication, which seems to be the FGF is the acronym that has kind of been accepted. We're going to be focused on printers with build volumes of 1/4 cubic meter and larger. So we'll cover some of the machines, their costs, practical applications, some design considerations, resolution impacts, and the economics of printing at this scale. Like she said, feel free to ask questions anytime. I'll be happy to back up if needed. Okay, slide. So the LFAM category can be kind of hard to define. Some people consider a 300 by 300 by 300 millimeter build volume to be large format, but that's only 0.027 cubic meters. And there's many desktop machines that now have those specs. So I make the cut at 1/4 cubic meter. The world's largest printer has a print volume of 1,566 cubic meters. So this is scaling up desktop printing. A lot of these machines are using a 2.85 millimeter filament, but some are running 1.75, and they use a high flow hot end to deposit material faster for really large parts. FGF, on the other hand, uses plastic pellets, as shown in the bottom picture. These pellets are similar to injection molding, allowing for higher material throughput and lower costs. Commercially available pellet extruders range from about 1 kilogram an hour up to 225 kilograms per hour. The choice between FFF and FGF really depends on your part size, material needs, and budget. So in the 1/4 to 1 cubic meter, these are typically gantry style machines. I mean, there are some Delta configuration printers, but I don't know of any that are larger than 1/4 cubic meter. All FFF machines are similar in how the part is created. Materials laid down layer by layer through a heated nozzle, same way a desktop machine works. The difference is really in the extrusion rate. Desktops typically extrude 10 to 30 cubic millimeters per second, while in LFAM, the extrusion rate is up to 200 cubic millimeters per second. There's some very well-known names in this segment, such as Stratasys, Big Rep, and Modix. But there's also a lot of small manufacturers. The machine on the left is manufactured by Luke's Laboratory from Wrightstown, Wisconsin, and that's priced around $20,000. He's got a nice business going down there. Big Rep sells their studio machine for about $60,000, and the Modix Big 120X, which is a kit, starts at $12,000. Stratasys machines are very well known in the industry, and they're known as the most push button printer, but they are expensive, significantly more expensive than these. And there's a wide range of features depending on the manufacturer, model, and capabilities. So the 1 cubic meter market is also typically a gantry style machine with filament or pellet, or a hybrid machine. Hybrid can mean many things in this industry. Some people, that's combining a filament and pellet printing, or it's combining pellet printing and a router head. Pictured here is our Compound Dynamics RMC30X. This is a 1 cubic meter build volume. We use Yaskawa CNC servos. It has a heated cabinet, heated filament storage, water cooling, onboard Windows PC, so models can be sliced and programmed right at the machine. This machine can output 200 cubic millimeters per second with filament and over 500 with pellets. Price on this machine ranges from $140,000 to $205,000. There are dozens of manufacturers in this segment, such as 3D Systems, Juggerbot, Big Rep, and several Chinese brands. Prices in the 1 cubic meter, they do range from as low as $10,000, which is an open air, very lightweight machine, up to $250,000, possibly more. So this is getting into more large format. Our size 40 machine is a 2.25 cubic meter. It's possibly the largest fully enclosed heated chamber machine available, but there's always somebody new. Here in the left photo, you can see this silver dry air. This is the pellet hopper. So all machines that are running pellets, they need to have a hopper for drying out the material. We mount it on the side of the machine to reduce the floor space. This is a 15 kilogram hopper. This is a dry air Arid X10 desiccant style dryer. With the door open here, this is the dry filament storage cabinet. So you have to have dry materials when you're running a large print. Nylon is terrible. If an open air nylon will run about 2 hours, then you can't print with it. Prices on this machine range in the $220,000 to $305,000. End of arm robotics are becoming much more popular. It's a growing segment, probably because of their versatility and very large build volume to price ratio. The two most well-known names in this segment are Seed and Caracol, although there's quite a few others. They can be programmed to work with standard slices, but typically they're using a 5-axis slicing software such as AI Build, so they can do non-planar printing. Prices in this range from probably the low end is $125,000. The system on the right is in excess of $500,000. The big advantages with a robot arm is you can do non-planar printing. You have very large envelopes, and your ability to utilize a router head on the same machine. I believe in the back of this photo on the right, that is a router head on a stand, so the robot can go over there and switch heads. The disadvantages of robotic arms are the overall accuracy. They are very, they will follow a tool path, but your actual positioning of the extruder head is not as accurate as a gantry style. And all of these machines print in open air, so they have to have materials that have the ability to do that. Material developments are continuously changing, and they've come up with some formulations that work very well. Whoops. So Cincinnati Incorporated actually produced the world's largest 3D printer through a collaboration with Oak Ridge National Labs in 2014. The print volume of this series went up to 8 foot by 8 foot by 22 foot with pellet extrusion rates of about 50 pounds an hour. So Cincinnati pioneered the mega-sized large format 3D printing. Unfortunately, they exited the market in 2022, and they no longer produce anything in additive. And a lot of that is due to this company. Thermwood developed the technology at a much faster pace than Cincinnati. They offer a large variety of machines. They were actually a CNC router manufacturer, so they were able to incorporate printing with routing and create hybrid machines very quickly. Their product range starts at a 5 by 5 foot table with a bed slinger style, and their largest machine to date is 15 by 40 on the X platform. Pricing on the smallest machine starts around $300,000, and you can see in this photo they're demonstrating printing vertically. So they've kind of turned it on its side. they started with the print here, and they're moving the bed and printing vertical. Ingersoll Corporation holds the record of the world's largest composite 3D printer built to date. This is the Masterprint 5X. Specs can be a little difficult to look up. I found the x-axis listed as either 22 feet or 32 feet, 96 or 100 feet in the y-axis, and 10 to 18 feet in the z. But it is a phenomenally large machine. This one's at the University of Maine. They're currently printing at a 500 pounds of material per hour rate. Their goal is to hit 1,000 pounds per hour. They're utilizing these machines for, a lot of it is government contract, boat hulls, wind turbine blade molds, and other supersized prints. This machine is priced in the millions. We can't talk about LFAM without talking about concrete. There are larger printers than the Masterprint, but they are not in the composites category. They're using a concrete mixture to print buildings, houses in a layer by layer system that's very similar to composite extrusion, but a very different medium. So in the applications, this boat was printed at the University of Maine on the Masterprint 5X. You can see it in the background there. And their material that they used was a composite of polymers and wood cellulose. So they're getting into the sustainable side of it also. Total print time for this was only 72 hours with a total weight of 2.2 tons. So at the time this was done, I think it was 2019, it was the largest solid 3D print ever produced. They've produced 2 more. In fact, I think they just finished one last month. The university is also using the machine to print shelters for the military, bridge molds, wind turbine blade molds, etc. Engineering prototypes is still probably the most common use for large format. This is a filament print being done on our RM30. We produced 2 of these to do a test fit and function of the parts for a local company before they invested in final tooling. This is a 1.8 millimeter nozzle with a 0.6 millimeter layer height. Total print time on this was about 28 hours, and this was done with filament. There is also final use parts. This is a stator and housing for a hydroelectric power plant in Wisconsin. Cadence LLC is located in southern Wisconsin, and they are pioneering low head hydro for smaller applications. It's really a neat group of guys, and they're doing some pretty interesting things. The material for this is carbon fiber ABS printed with a 2 millimeter pellet nozzle. There's also final use tooling. This is a punch and die for forming 040 aluminum knee braces. These are nearly solid and took days to print. But the total cost of the print was less than the cost of the billets of aluminum they typically produce these from. So, it was very economical for them. This is short run production. They took a long time to print because they were done with a 0.6 millimeter nozzle due to the fine details. It probably would have been more economical to produce them with FGF to a near net shape and then clean up the surfaces in a 5-axis mill. Or actually, you could have done these in a 3-axis mill because they are all straight down. But this is a good example of short run tooling. They can actually run a few hundred parts with these PLA dies. Prototype. This is a prototype vacuum mold being done by one of our customers. This customer was purchasing 90 wooden prototype molds a year. And due to the heat of the process, they were only able to form about 10 parts on the wood mold before the mold was ruined. It would delaminate. So we did some work with them on using ABS carbon fiber, and this material, they can do 50 prototype parts before the mold is shot. So it's a big advantage for them. Their final tooling that they make a mold from is made from aluminum billet, but the 3D printing allows them to produce the tooling in-house, resulting in a lot shorter lead times, faster development, and better performance of the product. Their payback on this machine is only about 18 months, so very economical. Furniture. So there are several companies out there now producing 3D printed furniture. I think most of them are using robotic end arm tooling. The advantage is, the ability to produce never before seen shapes, tailor to sizes to individuals, and produce on demand, ship local. Pricing on these is typically in the high-end furniture category, but I think that's going to be coming down over the years as material prices and technology advances. And UAVs. 3D printing is great for fast design development and complex shape productions. So UAVs can be quickly, cheaply, and produced on site for many applications. It provides great advantages over traditional manufacturing methods. A large printer can be located nearly anywhere and produce the structural components as needed. That really isn't possible to do with a large injection molding machine. Materials, LFAM uses filament and pellets pretty much. When printing a very large model, the material cost becomes significant. Printing with pellets opens up a lot of opportunities for cost savings. With prices around 1/10 that of filament, large models become much more economical, and the more quantity of pellets you buy, the lower the price goes. There's a lot of testing taking place to utilize the lowest cost materials available, and mixing like an injection mold grade, which is high volume and low price, along with a additive manufacturing grade at a 50-50 ratio to reduce the cost of materials more. Not going to talk too much about materials unless someone has questions. There's hundreds available. So on resolution, you got to think bigger when you're doing LFAM. So for printing large models, the number one thing you can do to reduce the print time and cost is increasing the layer height and the nozzle size. So a desktop is going to have nozzles of a 0.2 to 0.6 millimeter diameter. 0.4 is most typical. Layer heights are going to range from 0.1 to 0.3 millimeters. That's great for creating small detail parts, but result in large parts taking excessive amounts of time, think hundreds of hours. Our machines run a filament extruder with range of nozzles from 0.6 up to 2.4, printing much thicker, stronger walls with increased layer thicknesses and high deposition rates. Selecting the largest nozzle size that will work for your model is the way to get your time down. The pellet extruder has more than 3 nozzle sizes. They start at 1 millimeter. They run 3 millimeters, most typical, and 5 millimeter on our machine. And the wide spread of sizes means you have a wide range of resolution to choose from. Generally, your layer height is going to be 20 to 80% of nozzle diameter. We've done some that was 100%. This allows for a lot of range when programming. Here's what those nozzles look like in real life. You can see the desktop nozzles on the left side. The copper colored ones are the filament, and the silvers are the pellet extruder. So resolution, think bigger. The thicker the layer is, the fewer layers there are to be printed, and you can have a quicker model to produce. So Baby Groot on the right was printed with a typical 0.6 nozzle and a 0.1 layer Z resolution. You can see the fine detail this produces. Even the tree rings and the feet are distinguishable. But this level of detail really comes at a cost of time. Detailed Baby Groot is about a 12-hour print. On the left is the exact same model printed with a 1.8 nozzle and a 0.9 layer height. You can see the overall shape is definitely identifiable, but the details are lost. So but this is only a 1 hour print. So you have to select the resolution that produces desired results for what you're producing. Now, if you scale the baby Groot up 600% and the layer height were set to 0.6 millimeters, the details would be equivalent with the larger nozzle and layer height. And print time of this model would be about 36 hours. Printers with very high extrusion rates also have much larger nozzle sizes and print much thicker layers. This is the Strati, the first 3D printed car, being printed on a CI BAM, half-inch nozzle and about a 3/16 inch layer. The resolution is not the most attractive. Here's the finished product. There was some machining done to fit the lights and other hardware and to clean up the hood, but the overall surface was left as printed to highlight the manufacturing process. Nearly all models completed with high extrusion rates are going to be machined for cleanup. They are really a near net shaped part. All printing has similar considerations for layer time and cooling. If your layer times are too short, the previous layer may droop. And if your layer times are too long, it may be cooled down to the point where adhesion is poor, resulting in delamination. So here's a closer view of that bolt that was pictured earlier. You can see a marked difference in the surface finish. Things have advanced a lot in the last 10 years, but the surface is definitely not smooth like a typical fiberglass bolt. So the adoption of as printed large objects is going to take some time. You know, how suitable would this surface be? How suitable is this surface finish for a lot of other applications? The printing workflow for LFAM is pretty much the same as a desktop. Bed prep may be very different. In the really large format, some machines utilize a sacrificial bead board, or they'll print directly on plywood or directly on aluminum. So being a very large format does have its own challenges. So into a case study of how to design for a larger format print. Here's the original handle that was presented to us by the designer. You know, it looks good. It was designed for a specific purpose. The fine features of the thread required the part to be printed with a very small nozzle and a small layer height, and it had to be printed vertically, which also slowed things down. We were able to print it, but it took too long. This is the mating part with that. The grill slot profiles and the fine thread required a lot of passes, but it's very printable with a fine resolution. But one of the requirements was to print a pair in less than 2 hours. These initial designs took about 10 hours to complete. So this was a challenge. You know, we couldn't speed up the printing enough to meet the print goal. So what we did was got into we were trying to print this with a 3 millimeter pellet and a quantity of 8 parts at once. And, you know, we're not sure what went wrong here, but obviously not a very producible design. So it was redesigned to print effectively with large format. So we targeted a 1 millimeter layer height. The big coarse 2-lobe tapered thread engages much easier than the fine original thread, holds apart very well. It's also tolerant to variations due to material shrinkage. We added flats on both sides of the handle so it can be printed laying down. And the grill slots were removed from the model, and they'll be handled with just infill to produce an equivalent free area. And here's the redesigned parts. You can really see how thick the nozzle lines are, and the layers are very visible. But the print time for this for a pair was 1 hour and 24 minutes, and we expect that we would be able to get that down to about 1 hour per print. 8 of these fit on the bed so that multiple sets can be run at a time. It's really a great example of short run production. Another case study is an industrial process fan. This is a sheet metal part. They only produce about 100 of these a year. So they're looking at printing as a way to streamline production. Problems are the horizontal sections require support material, which would have to be removed. The offset hub is lifting all the vanes off the table, and strength considerations with the thin blade. It's certainly printable, but it's not going to result in a usable part. To make this a functional plastic part requires a very different approach to the design. Here's the last iteration optimized for a pellet printing application. It will print in about half the time of the original. And as you can see, the blade sections have been thickened for strength. The gussets are blended into the blades, and the blades are curved in 2 dimensions to increase their rigidity. The design flexibility of 3D printing really allows you virtually free added features. Blade thickness was set at 2 times the nozzle width to create a smooth and strong outer shell, and the angles were set so no support material is needed, and the one side is sitting directly on the bed. We have a lot of options to increase strength on this also if needed. And here's the first print of that model. Printed very well with good accuracy and no warp. One thing that's interesting, you can kind of see where there's a change in the perimeter layers, and they show up as these lines on the outside of print. That could be tuned out. This is something a little more fun. We designed a lounge chair, and here's our design. We started with a sphere. We made a bunch of revolution cuts, sliced some off, added a few lofts, kept angles under 60 degrees. Looks pretty nice, but is it going to be strong enough? Hidden inside, you can see the design brings the 2 outer walls together to provide more strength in the seating area. The left is a section view done in Inventor. You can see it's created as a solid and it's printed in base mode. This is how most of the 3D printed furniture manufacturers are approaching these designs. Here's a better view of it as it's printing. The wall thickness is about 1/8 of an inch. Just one big base mode print. And total print time was about 12 hours with printed with PETG filament. Material cost for this piece is about $300. We plan on printing another version of this with our 3mm pellet extruder and recycled PETG or possibly PLA. Material cost in that process is going to be under $60, and the print time should be cut in half, which makes it much more viable from a commercial standpoint. So let's talk about economics of large printing. Your FFF filaments are costing between $20 to $200 per kilogram. FGF pellets are $2 to $20 per kilogram, up to 10 times cheaper, and it's really because they skip the filament production process. FGF's high throughput can be 1,000 times faster, but that's at the cost of resolution. For a 1/4 cubic meter part, FFF might cost $500 to $1,000, take 50 to 100 hours, while FGF could cost $100 to $300 and take 5 to 10 hours. Significant cost savings. With near net shape prints, post-processing like milling or sanding, it does add cost, but it's often minimal depending on the size. LFAM really saves money by eliminating the traditional tooling costs for production of unique models. So what's the future of additive manufacturing and large format look like? We're seeing improved FGF resolution, new high performance materials that print better in open air with reduced warp, better layer adhesion, better strength. and a real push for sustainability by using recycled and bio-based pellets. Overall, the AM market grew in 2024, and it is expected to continue the growth trend as more industries are continuing to adopt this technology. The industrial machine market is projected to have a very good year after a decline in 2024.